So today we're going to talk about characterizing active learning environments in physics, aka the last 6 years of my life. So let's get started. So an overall outline of where we're going today, we're going to start with some background information that's relevant to understand what's going on. So we start by talking about what is active learning, and then some network analysis, our classroom observation protocol called COPUS, latent profile analysis. And then my dissertation was structured in a collected papers model. So I also structured the presentation in that way as well. So we'll talk about each of the 3 papers and their individual results, and then we'll discuss it all together and wrap it up. So to start, we have active learning in physics. So what is active learning? So active learning has evolved into being this catch-all phrase for any curriculum that's not lecture, but it actually has a very specific definition when we talk about active learning in a research sense. So there's a more exhaustive list of qualifiers, but they can be summed up as 3 main components. Students are engaged in the learning process. So this can manifest in numerous different ways, so long as the student is not just sitting and passively absorbing information like we typically get in a lecture setting. The second is that the pedagogy is the result of deliberate research into the teaching and learning of the subject matter. And the last is that this pedagogy is continuously refined and improved through research on live implementations of this pedagogy. So there are several active learning pedagogies that get used in physics. And in this study, we take a look at the 6 most prominent ones as identified by our new faculty workshops that are put on by the American Physical Society and the American Association of Physics Teachers. So those 6 pedagogies that we look at are tutorials in introductory physics is our first one. And this is a pedagogy that occurs in a standard large enrollment course because it was developed at the University of Washington, which has several thousand students in their introductory sequence. So this is usually broken up into a lecture, a smaller tutorial, and lab components like you typically see in a large university. The tutorial section, which is very similar to a recitation section that we do at Drexel, is where the bulk of this pedagogy occurs. So students are working in small collaborative groups on scaffolded worksheets that lead them through activities that confront common misconceptions that come up in physics. So they work through a problem and they have a TA that goes around and helps guide these discussions. The next one is ISLE, which stands for the Investigative Science Learning Environment. So ISLE is designed to have students learn physics in the same way that practicing scientists learn new things. So students are led through this knowledge construction cycle that's based around observation and experimentation. And a diagram of that learning cycle is shown in this figure. So this typically starts with an observation experiment where you learn to identify patterns and use your representations to kind of explain what you're looking at. And from there, you can come up with different hypotheses and explanations. And then you test those hypotheses and rinse and repeat. Now, ISLE can be integrated into an entire course, which has an interactive lecture, recitation, and a lab component. But it can also be used as a standalone lab environment. And so we actually look at both cases here. Our next pedagogy is modeling instruction. So modeling instruction focuses on building conceptual models about physics from the ground up, and then using and testing those models until they can't work anymore and they have to make a new model. So modeling instruction is done in a large studio environment. So it's a large open room with tables, and students are working in groups to work through these activities. And one of the unique features of modeling instruction is that they also have class-wide discussions known as whiteboard meetings. So each group has to kind of summarize their activities that they did and then bring it to the class and presents their results to each other. Our next one is peer instruction. So peer instruction, I like to call it the gateway active learning because it can be implemented into a standard lecture environment fairly easily. And while most people think of peer instruction as, oh, I'm using clicker questions in my lecture, peer instruction specifically refers to a cycle of instruction. So it's not just clickers, it's an actual deliberate cycle, which starts out with a short lecture on a concept that's about 5 to 7 minutes long. And then students are given a concept test question and asked to individually answer it. So this is usually facilitated with the clicker questions or your personal response systems. After they answer alone, they then discuss with their peers and try to convince each other that their answers are correct or incorrect, and then they vote again. And the instructor is able to really keep an eye on real-time understanding of a concept so that if the students don't answer correctly, they can go over the topic again. And if they do answer correctly, the instructor can say, haha, they understand, and move on to the next concept and repeat the cycle again. Our next one is the context-rich problems, which is sometimes referred to as the Minnesota model because it was developed at the University of Minnesota. So context-rich problems is also in this Minnesota model for a large introductory physics course. So it still has the interactive lecture, recitation, and lab format. It's a slightly different in that it uses cooperative grouping in the smaller sections. So students are working together on these problems. And the problems in particular, every single problem that the students encounter has a real world context. So instead of being like, find the acceleration of the block sliding down the ramp, it gives a story behind it and it gives extraneous information so that students have to really think about what's going on and parse through the extra information. The instructor uses an apprenticeship model to show the students how to solve problems. So this is sometimes also referred to as like the I do, we do, you do cycle, if you're familiar with that terminology instead. So in the lectures, this instructor is really walking through the problem solving process, thinking out loud, showing students how they approach this. In the recitations and the labs, they get to work together with the help of a TA. So they're doing it together, and then in their homework, they're solving them on their own. And then our last pedagogy is Scale Up, which stands for Student-Centered Activities for Large Enrollment Undergraduate Programs. So this is an environment that's designed for multiple active learning implementations, and it really helps integrate the lab and the lecture into a large studio environment. So a scale-up classroom looks like the figure pictured, and that is large, open, it has large round tables, it has a lot of technology that the students can use. And while it's not its own specific pedagogy, it is a unique environment that can implement any pedagogy it wants, really. So we treat it as its own unique pedagogy in this case. So after looking at all of these pedagogies and these active learning pedagogies in physics, it makes us really think like, well, what makes these unique aside from just not being lecture? Because the majority of studies into these pedagogies compares them to lecture, and we really need to move away from that comparison and start talking about why is this useful? What parts of this curriculum make it good? And that's what we're really trying to answer here. So active learning is inherently social. And how do we measure socialness? How does this pedagogy influence the socialness of the classroom? And we need tools to do this. So when we think about how to measure social interactions, the first thing that comes to mind is social network analysis. And how does the pedagogy influence this? We need to observe what's going on in the classroom. So the tools that we use are going to be network analysis and classroom observations. So then we can talk about our specific research questions. So how does COPUS and the student network metrics distinguish active learning pedagogies in physics? So COPUS is the observation protocol that we used in this study, which we'll discuss shortly. How can differences among active learning environments be characterized through these classroom observations? And to what extent is that network development associated with particular curriculum features? So let's talk about network analysis. What is it and why are we using it? So network analysis is used to study relational data, and active learning is social. Students are talking to each other and learning physics, and therefore it is relational. And we can use network metrics to describe the structure of these student relationships that come about due to the active learning environment. So let's talk about what these different terms are. So we have a node. So the node is the object, person, or the thing being connected in this network. For this example, I'm using cats. Shout out to my cats and my mom's cats. So each node can be visualized as a dot in the network. An edge is the connection between those nodes. So if these cats have lived together, we draw a line between them, and that's called an edge. A sociogram is the resulting diagram. It's what the overall picture is called. So these networks can be undirected, where the connection either exists or it doesn't. The cats lived together. Or it can be directed, where that connection indicates who initiated that connection. So has chased is an example because there's very clearly one cat doing the chasing. There's a directionality to it. We can then talk about the density of the network. So the density is the ratio of actual observed edges to the possible edges that could exist if every cat was connected to every other cat. So here we have 11 edges and there are 36 possible connections. So our density is 11 over 36. A triad is any trio of nodes. And we care about triads because sociologists identify groups of three as really the building blocks of a group structure. And since we're trying to talk about how groups and interactions occur in a pedagogy, triads are really interesting things to look at. So there's lots of different triad types. There's a type 0 where there's no connections between the three cats. There's a type 1 where there's only one connection. Type 2, two edges. And a type 3, also known as a triangle or a transitive triple is what it can also be called, is where all three of them are connected to each other. Which brings us to another metric called transitivity. So your transitivity is the ratio of type 3 triads and type 2 triads. So in this example with our cats, there are 4 type 3 triads, there's 4 complete triangles. And there are 9 type 2 triads, which are here, 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 and here. So our transitivity is 4 complete triangles out of 9 type 2 for 0.44 transitivity. So this really helps describe the connectedness of the network and how, like, my friends introduce me to my other friends and we make complete triangles. Our next one is diameter, which is the longest of the shortest paths between nodes. So when you read that, it doesn't really make sense. So let's illustrate it a little bit. So to get from Turbo to Toby, we can take the red path, which is 6 edges long. But that isn't the shortest path. The shortest path between those two cats is this blue one, which is only 4 edges long. So we find the shortest path between any two nodes in the network, and the longest one of those is the diameter. So our diameter in this case would be 4. Then we have the giant component, which is the size of the largest connected cluster. So this network has a giant component of 8. Our degree centrality tells us how many edges are connected to a node. So if you have a higher degree centrality, you're connected to more people. And if you have 0 degree centrality, you're called an isolate. So that concludes our network terms that we're going to be using in the rest of this study. So now let's talk about COPUS, which is our classroom observation protocol for undergraduate STEM. So networks allow us to see how interaction patterns are formed, but what students do and teachers do shape those interactions. And so we need some way to measure that as well, which is why we use COPUS. So COPUS provides us with a series of codes to describe classroom behaviors. So we have a set of student codes that range from listening to the instructor to answering clicker questions to waiting around. And we also have instructor codes, which range from lecturing, writing on the board, administrative tasks, and so on. So from all of these codes, we can create a COPUS observation, which we do live in the classroom. So this is what a COPUS observation looks like. We have all of our codes across the top, and our time is broken up into 2-minute intervals. So we place an X in the column of the code if this behavior occurred during this time interval for at least 5 seconds. And then at the end, we can add up the total number of check marks in each column and create what's called a COPUS profile. So there's 2 ways to make COPUS profiles. We can either use pie charts or bar charts, depending on what we're looking for. So if you are more concerned about the breakdown of your types of activities, you would want to use a pie chart. So the pie chart takes the ratio of X's of that code to the total number of X's. So it's the ratio of occurrences of this code to all of the occurrences. So it forces it to be out of 100% of the codes. Whereas the bar chart method is ideal if you want to look at the portion of class time that's being dedicated to this behavior. So instead of taking the ratio of occurrences of this code to all of the observed occurrences, we take the ratio of occurrences to possible occurrences, so the total amount of time. So like our WG code was marked in every time interval, so it has 100%. From these COPUS profiles, it really allows us to see what's going on in the classroom, but from the naked eye, it's really hard to see how these profiles are different between pedagogies just looking at bar charts. So latent profile analysis helps us uncover those differences that aren't immediately obvious to the naked eye. So what latent profile analysis does is it helps us uncover hidden groups in our data. So if, say, we measured a variable and it gave us this red curve on the left, latent profile analysis says, hang on, I think there's actually 2 hidden groups inside this data. Let's figure out what those groups are. So the way that this works is using an expectation maximization algorithm and assigning fractional responsibility. So we're going to try to break that down a little bit because I know this looks really scary. So these R's are fractional responsibility. So this pi value here is just the proportion of the data that belongs to that group. This is the Gaussian that fits that with the mean and variances, and this is the same numerator but summed up over every possible group. N is our number of members in that group. So we sum up all of the responsibilities for each point for that specific group. So it's kind of like a soft average, if you will. This is our mean of that Gaussian. So it's the middle point of those groups. This is our variance covariance matrix, which looks like this. So your typical variance of a matrix of your Gaussian is along the diagonal, but because we're measuring this in multiple dimensions, we can expand that out into a covariance. So how does this variable depend on this variable within this group? So each Gaussian gets its own. And then finally, we can recalculate the proportion of members in these groups based on all of the previous metrics. And then we repeat again and again and again until it converges into distinct groupings. So now that background is over, we can jump into paper number 1. So the first paper was Characterizing Active Learning Environments in Physics using Network Analysis in COPUS. So this is really the overview paper of the project. So if we want to study these pedagogies, we need somewhere to study them. So we need to select sites that employ these pedagogies. So when possible, we tried to use the developing site. And if it wasn't possible, we took direct recommendations from the developers on where to go next, so that we had one site for one pedagogy. And our site demographics break down like so. So we have 4 four-year public schools, a 4-year private, and a 2-year public, ranging from 11,000 to 37 or to almost 50,000 students. And we also have a pretty decent breakdown in every other category as well. So I'll give you a moment to glance at these before we move on while I take a sip of water. Alrighty. So once we identified our research sites, we needed to collect that data. So we gave students surveys at the beginning and end of the term, and we distributed these via email using Qualtrics. We provided the students with a list of everyone enrolled in their class and asked them to choose who they spoke to from this list. So I will show you what that actual question is at the end. Okay. And for our COPUS observations, we conducted these in person during 1 full week in the middle of the term. So the question that we asked was, please choose from the list of people that are enrolled in your physics class the names of any other student with whom you had a meaningful interaction in class during the past week, even if you are not the main person speaking. And from these survey responses, we were able to construct our networks. So for your tutorials in introductory physics, if we look at our networks at result, we can actually see the grouping of these tutorial groups emerge in the network. So this is also a good place to point out that the coloring of these nodes, if they're orange, the student filled out the survey. So our response rate was not very great, as we'll discuss later as well. And for our COPUS observations, we have our lecture component that we observed, which was an interactive lecture. We still had large amounts of lecturing, but we also had some clicker questions and some follow-up discussion, as well as a demo. And in our tutorial section, our students are mostly working in groups on a worksheet or asking questions to the TA. While our TA is moving and guiding this active learning task, having one-on-one conversations, or waiting for students to ask a question before they interact. For our whole course implementation of ISLE, We look at the lecture component, which is still very much lecture and writing on the board with a couple of questions thrown in. And the recitation section, students are working in groups on activities, asking questions while the instructor is wandering around and helping and interacting, and also doing some administrative tasks like talking about the upcoming exam. The whole course implementation also had its lab component, where we can see these individual lab groups that students are working in, and lab activities were coded as other group activity. They were asking questions, listening to administrative tasks from the instructor. For the lab only implementation, so this portion of the course could be taken separately from the lecture and recitation. So they didn't necessarily have to take it in the same term. And again, we can see the lab groupings showing up in the networks with some branching between groups. And our students are mostly working in groups, asking questions to the TA. And in this case, we actually had very brief amounts of instruction at the beginning of the lab by the teaching assistant. So they do a little bit of lecture about the activity coming up and then do some administrative tasks such as handing back their lab reports from last week. In modeling instruction, we end up getting most of the codes lighting up for our instructor. So they're mostly doing some moving around the room, guiding instruction, talking to the individual groups of students. But there are occasional times where they need to clarify something if they're noticing a trend of students having misconceptions about something. While our students are working on worksheet activities, they're having whole class discussions because of those whiteboard meetings, and they're doing student presentations because they're presenting their individual whiteboards. And our modeling instruction network ends up being very tightly connected because of this class-wide interaction structure. Peer instruction, on the other hand, we mostly get lecturing, writing on the board, and we get a lot of clicker questions coming out of here because peer instruction is typically where these are employed. So we get our clicker questions, our posing questions without clickers, answering student questions. So our students are getting a little bit more involved in this learning process. And in our networks, we can actually see some of the peer instruction curriculum showing up as well, because peer instruction focuses on having you talk to your neighbor about the question at hand. So we see a lot of this stringiness show up as opposed to the clustering like we do in our small group pedagogies. Context-rich problems, we have observations for the lecture component, which is fairly interactive, uses a lot of clicker questions. Our discussion section is mostly working together in groups on a worksheet with a little bit of instruction as needed. And our labs are kind of the same way. So there's a little bit of instruction happening at the beginning, and the context-rich problems are unique in that they have students predicting what the outcome of their lab is going to be before they actually do it. And context-rich problems, we start off seeing a little bit of clustering, but then they eventually get pretty tight-knit towards the end of the term. And finally, we have scale up, which hits on every single instructor code that you can, which really shows the uniqueness of the environment and that you can do that. It's set up in such a way that you can use any curriculum that you want. And we see a lot of the large table structure really manifest itself in the network as well. All right, so now let's look at the actual network metrics that arise. So diameter is a metric that's limited by class size. That's that longest, shortest path between nodes. So the absolute value of the diameter shouldn't be compared. What we really want to look at is the change in diameter from the beginning to the end of the term. Most curricula had a change in diameter of plus or minus 1 to 2 students, which really suggests that the overall style of interaction between students remained largely unchanged from early to late networks, except for modeling instruction. We see a large decrease in diameter here, which is indicative of a significantly more tight-knit class community at the end of the term, which makes sense because modeling promotes not only in-group cooperation, but also brings those students together to discuss concepts with their whiteboard meetings. So this is fruitful in that a large decrease in diameter could be a distinguishing feature of modeling instruction. So average degree, on the other hand, is not as limited by class size. The average degree increased throughout the term for all curricula, which makes sense qualitatively. So as students become more familiar with their peers, they form more connections regardless of the curriculum choice. We do notice, however, that the largest gains in average degree occurred with modeling instruction with a gain of just over 3, scale up with a gain of about 2.5, and context-rich problems with a gain of just shy of 2. So the remaining curricula had gains ranging from 0.2 to 0.75, which averages less than 1 new connection per person throughout the term. So this makes us think that modeling, scale up, and context-rich problems are curricula that foster building new connections, but while still retaining the old connections made previously in the term. So with an increase in average degree, the density of connections increases in all pedagogies as well, because now we have an increase in number of connections, so we have an increase in the total connections throughout the whole network. But density is also directly correlated to class size, so we can't really make any conjectures about the pedagogical influence on this metric. Transitivity, on the other hand, so transitivity can be loosely described as the base level of collaboration between 3 students. And this increased for all curricula except peer instruction, where the transitivity remained approximately constant. So all the curricula have a focus on collaborative group interactions, with the exception of peer instruction, which instead promotes partner interactions. So this could be an identifying feature of peer instruction as well. But the spatial limitations of peer instruction may have inhibited that transitivity growth, since it's the only pedagogy that occurs in a lecture hall exclusively. So we can't say for sure that it's the curriculum that did this as opposed to the classroom. So we would want to dig into that deeper. In conclusion, from paper number 1, modeling instruction, we saw a large decrease in diameter. Peer instruction had consistent transitivity. Modeling, context-rich problems, and scale-up had a positive increase in average degree. But looking at our COPUS observations, all of the recitation-like and lecture-like COPUS look very similar at first glance. And we think that's largely because there's only 2 codes for group activities. You're either working in a group on a worksheet, or you're working in a group without a worksheet. So we really need more differentiation with our observation protocols going forward. So we couldn't see differences in COPUS this way. So let's try a different way. So this is where our latent profile analysis comes in. So we took those COPUS profiles and we ran latent profile analysis on it to see, well, what if there is some differentiation and we just can't see it? So as a quick reminder, latent profile analysis lets us tease out hidden groups from a data set. So here we want to use it to pick out the pedagogy from a COPUS code. So this is a 1D example. So in our case, the variable is that COPUS profile code that ranges from 0 to 1. So that's that percentage of class time. And then we want to pick out the groups, which are going to be our pedagogies. To do this, we used tidy LPA in R, which wraps to another package called mclust, which is only relevant if you know R. And then mplus in this table is proprietary software, so we did not use it here. So dimensions are the codes in this case. So in our covariance variance matrix, those are going to be our rows and our columns, our COPUS codes. We have a 25 by 25 matrix because there are 25 codes. So the variance tells us about the width of those Gaussians in that one specific code. And the variance, we can talk about the different models. So equal variance forces each group to have the same width in that one code. We end up choosing the equal variance models because we don't have enough data for varying variance. You really need to have a lot of data points in order to force those to be different from each other and really narrow down on that. So we don't use any of those models. The covariance tells you about how the codes depend on each other in the same group. So in peer instruction, these two codes depend on each other. The models that we can use in tidy LPA force these dependencies to be either non-existent, equal between groups, or varying between groups. So we can't do the varying between groups because we don't have mplus. And forcing those to be equal between groups is not appropriate. So that's really saying that like the relationship between lecture and group activities in this pedagogy is going to have the same relationship in this other pedagogy. And we can't really say that that's true. So we instead assume that there's no relationship between the variables in each pedagogy, which sets us down into model number 1. So equal variance and 0 covariance. So our COPUS data breaks down like so. In our previous paper, we had aggregated the modeling instruction and scale up. So a week of observations was in one profile, but here we treated them as separate observations, just so we're really clear about that. So we had, for our tutorials, we had 1 lecture observation and 19 tutorials. The whole class aisle, we had 1 lab, 4 recitations, and 2 observations of the same lecture. The lab only implementation, we had 5 labs. Modeling instruction, there were 3 sections with 2 observations each. We only had 1 observation for peer instruction, 2 discussions, 4 labs, and 2 observations of 2 lectures and context-rich problems, and then 3 observations of the same scale up. So when we ran our latent profile analysis, we did it for 2 profiles and 5 profiles. So to really decipher what you're looking at here, each code has its own slice. And this slice gets fit with those Gaussians that we showed in the background for the hidden groups. So if we kind of turn that on its side and think about what we're looking at, it's like a top-down view of those Gaussian fits. And we did the equal variance model, so these have equal widths. So those boxes are going to be the same width for each code. So our red group, we can see it has a lot more clicker questions, following up clicker questions, lecturing, and students listening, whereas our blue group has more one-on-one discussions and moving around the room and guiding student discussions. So if we turn that into a list What we really did was we separated it out into lecture-like environments and not lecture-like environments, which makes sense. You're lecturing in the lecture, you're moving around the room and guiding group instructions, and not lecture-like. In our 5-profile solution, just to kind of break out the unique pieces here, profile 1, our red group, really stands out. It keeps those clicker questions and that lecturing and students listening dependence. Group 2 stands out with student presentations. It's the only one that had that. The whole class discussions, and it was mid-level with students working in groups, whereas the other pedagogies were really split. Group 3, which is our green one, really stands out with group 4, and that groups 3 and 4 have high levels of other group activities, but group 3 and group 4 differentiate from each other because group 4 has that predictive aspect that the students do as well. And then group 5 has the highest levels of group work with worksheets and moving and guiding around the room. So if we turn that into list form, that breaks us up into lecture-like, which is our group 1, modeling instruction, which had the whole class discussions as the identifier. Our IL labs broke off, and so did our context-rich problems labs because they had that predictive aspect. And then everything else that looks very similar to a recitation was left in profile number 5. If we look at our Bayesian information criterion, so this really tells us like the goodness of the model is how I like to think about it. So the reason we chose 2 profiles is because it's the simplest solution we can look at. And then 5, 6, and 7 really had the best BIC. So we chose the simplest model of these 3 because they were about the same. So our paper 2 conclusions is that it works. Let's extend it. So this was a successful proof of concept. It actually separated the COPUS profiles based on the course components. We still need more data to make specific claims about pedagogies as a whole. And one of the issues that we ran into was that it separated it by components, but we wanted to separate by pedagogy. So in order to do that, we need to think of a good way to group those COPUS profiles to really represent what does this pedagogy look like as a whole, instead of separate lecture, lab, recitation observations. And our last paper is actually going to be pretty brief. So this was, we wanted to combine these 2 different approaches to measurement, these 2 approaches of measuring active learningness. And one of the ways that we think we can do this is with exponential random graph modeling. So we did a small pilot project. This is not a complete study. This is going to be extended moving forward by another student. But just a quick breakdown of what happens here. So an exponential random graph model is essentially the best fit for network graphs. So networks are built on these interconnections, and these ergms allow multiple inputs for network features to fit. So you can fit based on number of edges, the number of triangles, some node attributes like your gender, age, or major, or network-wide attributes like what pedagogy are you, or what COPUS profile, what your COPUS profile looks like, which is why ergms are really exciting, because we can take the network aspects and the COPUS aspects and smush them together to really talk about, does the COPUS drive the network development, or is it just random? So the way that this works, we talk about dyads here. So previously, this structure was known as a type 2 triad, but we call it a dyad here because this dyad shares 1 partner, as opposed to this dyad shares 2 partners, which makes a square instead of a triangle. So that's just an extra level of terminology for you. So what we do with ergoms is we can fit an observed network. So we did this with peer instruction. This is our null hypothesis. So every edge between our nodes is equally likely. So there's no structure. We just randomly spatter some edges in there. And we take that model and we simulated 100 networks using that model. And we plotted the number of edges that showed up versus the number of single dyad shared partners. So that's what we're looking at here. And the red line is the actual value from the actual network, whereas these are the simulated networks. We then decided to look at an edges plus a single dyad shared partner model. So this says that if this edge is going to make a dyad shared partner, then it is more or less likely to happen. So it tweaks that probability of the existence of an edge based on some conditions. So when we did that and plotted it with our actual value, we get a much tighter simulation. And then we also looked at the edges and triangles model. So if this edge will complete a triangle, it's more or less likely to happen, and compared to our observed value. So number of edges is our top row, and the number of dyad shared partners present in the network is our bottom row. So just by looking at this, we can see, okay, so by chance, triangles are more likely to happen than what we observed in our actual network, whereas the number of dyad shared partners might be an indicative feature of this peer instruction network. So this is a pretty exciting way forward, figuring out how these different structures either happen by chance or are caused by these different attributes. So let's tie it all together and wrap up. So if we compare our network metrics versus latent profile analysis, we notice some signatures and trends. So modeling instruction had a decrease in diameter, it had that more tightly connected network. So that could be a truly identifying feature of modeling instruction. However, modeling instruction was not the first pedagogy to split off with latent profile analysis. It was actually the context-rich problems, which were the first ones to differentiate from the not lecture-like in the 3-profile solution. The average degree increased for modeling, scale-up, and context-rich problems. So are these identifying features of these pedagogies, or is it something else? So latent profile analysis suggests something else, because scale up never separated away from the lecture-like environments, whereas context-rich problems did, then IO labs, and then modeling instruction. We can then also look at our recitation-like environments. So context-rich problems showed that higher increase in average degree, while the similar courses that latent profile analysis bunched them with didn't. So context-rich problems had similar group sizes compared to tutorials and IO. But if we compare these networks, tutorials really keeps that group structure, so does IO, whereas context-rich problems ends up being a very compact class-wide network. And so we think this might be because context-rich problems, students rotated groups frequently as indicated by the instructor, and they had a smaller overall enrollment. So by the end of the term, most students had been in a group with at least a quarter of the other students in the class. And this actually manifested itself in our observations as well, because I would notice that the students would frequently discuss their data with adjacent groups without being prompted to do so. Whereas the IL and tutorial students were hardly seen speaking with students outside their assigned groups in class. We can then also talk about, is it the environment that's forcing this network structure, or is it the pedagogy itself? So modeling and scale up are both studio based. They both use large group interactions, but modeling instruction had much tighter, closer knit networks, whereas scale up retained the cluster in the networks. So this makes us think that these are separate manifestations of the pedagogy in the network, because both of these use cooperative grouping and they both use class-wide discussions, but they have very different network structures. And latent profile analysis picked up on this difference as well, because it consistently binned modeling instruction and scale up as different. And I think one of the biggest differences between these two is that scale up really still used lecture as the main method of information transfer, with a large uses of clicker questions, whereas modeling instruction transferred information through exploration and discussions with your peers. Similarly, we have peer instruction where the transitivity stayed largely the same, where peer instruction focuses on those discussions with your neighboring peers rather than cooperative grouping. And we found signals of this using the exponential random graph models as well, where it had that dyad shared partner dependence. So it had that string, the type 2 triad, as opposed to the complete triangle, which makes sense because it's a lot easier to talk to your neighbor than it is to lean over and talk to the person on the other side of them. I do hesitate to identify low transitivity as an identifying feature of peer instruction, though, because it was the only pedagogy we observed where the main curriculum was deployed in that lecture hall. So the geometry of the room with its rigid and tiered seating arrangement could very well be artificially constraining those student interactions and thus the network structure. Right. So we also ran into some limitations using COPUS. So we chose COPUS because it was easy to implement in a live observation. Our cooperative group activities were really limited to only WG, so working in groups with a worksheet, and OG without a worksheet. And this really manifested itself in our latent profile analysis as well. So it could not tell the difference between tutorials, IL recitations, and context-rich problem discussions. So that makes us think, are these not as different as we think? Or do we need more codes to really dig into what the differences between these are? We also need something where we have an other instructional versus other non-instructional, because we had a few situations where an instructional activity got binned in the same code as like eating your lunch because you don't have a lunch break. With our network data, our data collection was really limited with the survey distribution and response rates. So some of our instructors delivered the network survey during class, which significantly boosted the response rate, while other instructors just left the dissemination up to us via email. So a lot of students were under the assumption that it was spam and deleted it, while others simply ignored this message as it wasn't really directly impacting their course experience. And I actually did have students tell me this, so I'm not making this up. We were also limited by the limitations from the IRB, which disallowed us to include students under 18. So even though they filled out the survey, we had to remove their data. So to help combat some of this missing data from lack of response and removing our under 18 respondents, we used the undirected network because it's more robust to missing data. So even if I don't fill out the survey, if you name me, I'm still included. But we do miss out on a lot of really interesting things, such as the directionality, some weighting of the edges. So how often do you talk to these people? So figuring out how to increase and get a complete network is really a top priority going forward. We also didn't have consistent census boundaries. So peer instruction, for example, we surveyed at the lecture level and essentially pretended that the recitations and labs didn't exist, even though they were significant portions of the course. Whereas in ISLE, we took the surveys at the smaller discussion or lab level. So being consistent with these would also be beneficial going forward. Using our COPUS data, having the observations as separate course components, we weren't really able to capture the same face-to-face time as the networks would because these were done in person. So we were really limited to what we could see during 1 week of observations, and they were in the middle of the term as opposed to the beginning or the end of the term as well. And we also don't have a COPUS for every corresponding network because some of these courses were happening at the same time, and I can't be in 2 places at once. And we also have a very small amount of data also. So for future work, we want to focus on getting that high quality data collection, more data, and then we can really start looking at secondary and tertiary implementations as well as partial implementations of a pedagogy to see how much this differs. We'd like to expand the exponential random graph modeling research, which is actually being started right now by another student, and get more data and either use a supporting observation protocol to go with COPUS or a different one, because there are a few observation protocols that have popped up in the last year or two that we think could be really interesting and get those differences as well. And that's it. Thanks everybody for coming to my defense. I'd like to thank NSF for funding this research, Drexel for hosting me, Wright State University and Adrian and Eric and our Physics Education Research Network group and our course instructors, our survey participants, and then everybody who's been there for me along the way.